Today we're going to start Chapter 8, which is about quadrilaterals and polygons, and specifically we're going to go over Lesson 8.1, which talks about angle measures in polygons. So today we're going to learn a few new terms. We're going to review some old terms that we learned earlier this year, and then we're going to learn a total of 3 theorems and corollaries about angle measures in polygons. So let's take a look at polygon A, B, C, D, E, F. The first term that we're going to learn today is called consecutive vertices. And these are 2 vertices that are endpoints of the same side. So for example, vertex A and vertex B on our polygon would be considered to be consecutive vertices. And they're not the only pairs of consecutive vertices on this polygon. There are many others. For example, vertex C and vertex D. Those are also consecutive vertices. So again, they're just 2 vertices that are endpoints of the same side. They have to be on the same side of the polygon. Another term that we're going to learn today is the diagonal. The diagonal of a polygon is a segment that joins 2 non-consecutive vertices. So a polygon can have many different diagonals. For example, if we were to take a look at segment AD, that is connecting 2 non-consecutive vertices. It is connecting vertex A with vertex D and is inside the polygon. So therefore it is considered to be a diagonal. And again, there are many diagonals that can be contained within a polygon. We can also have the diagonal BF. Vertex B and vertex F are non-consecutive vertices, so therefore there is a diagonal that can be drawn that joins those 2 non-consecutive vertices. Lastly, on this slide, we're going to refresh your memory about a regular polygon. So as you may recall, we talked about regular polygons earlier this year, and specifically a regular polygon is unique in that it's a polygon that is made up of congruent sides and congruent angles. So all of the sides of a polygon have to be the same length, and all of the angles of that polygon have to have the same interior measure for it to be a regular polygon. Okay, now that we've learned a couple of new terms, we're going to move on to theorems and corollaries about angles of polygons. And the first 2 theorems that we're going to learn, or actually it's a theorem and a corollary that we're going to learn, is regarding interior angles. So let's quickly review what an interior angle is. If we take a look at our pentagon over here and see what an interior angle is, we see that it is on the inside of the pentagon and it is located at the vertex. So that's what interior angles are. They are just simply inside of a polygon and they're located at each vertex of a polygon. So the amount of interior angles that you will have in a given polygon is determined by the number of sides. Now let's find out about the theorems with regards to angles of polygons. The first theorem that we have is the polygon interior angles theorem, which states that the sum of the measures of the interior angles of a convex n-gon is n minus 2 times 180 degrees. Okay, so let's quickly review a few terms here. We've got in our theorem a convex n-gon. So if you remember from earlier this year, we learned that convex polygon means that all of the interior angles are less than 180 degrees. So our pentagon that we have over here, this is a convex polygon. All of our interior angles, so our angle measure right here is less than 180, this is less than 180, and so are the remaining 3 angles. They are all less than 180 degrees. So that means that this is a convex polygon. And now we have the term n-gon. N simply refers to the number of sides. So for example, our polygon over here has 1, 2, 3, 4, 5 sides. So n would equal 5 in this case. And in fact, if we were to plug this into our equation that we have to figure out the sum of the interior angles, that means we would plug in 5 for n, so we would get 5 minus 2 times 180 degrees. And when we multiply all of that out, we would find out that every polygon that's 5-sided would have a sum of 540 degrees for their interior angles. a corollary that corresponds with this theorem, which is the interior angles of a quadrilateral. And this corollary specifically states that the sum of the measures of an interior angles of a quadrilateral is 360 degrees. That will always be true no matter what type of quadrilateral you will have. And we could actually expand this corollary if we wanted to into any type of polygon, because the number of, or the sum of the interior angles of any polygon will always remain the same. So for a triangle, it will always be 180 degrees. For a quadrilateral, it will always be 360 degrees, and so on and so forth. All right, now we're going to move on to the last theorem of this lesson, which talks about exterior angles. So let's quickly review first what exterior angles are. If we were to extend the side out of our pentagon like we just did, that angle that is formed by extending the side out is the exterior angle. So that is what we are talking about for our polygon exterior angles theorem. And we can extend the sides out of our polygon for every single one of these sides. So for example, if we were to extend this side out right here, this would also be our exterior angle. If we extended this side out, we'd have an exterior angle here. And if we extended this side out, there's another exterior angle and one more side that we can extend, and there's an exterior angle. So we have in total 5 exterior angles that we would sum up here. Now looking at our polygon exterior angles theorem, it states that the sum of the measures of the exterior angles of a convex polygon, again, we have that same type of polygon, convex, so but all of these theorems and corollaries only deal with convex. And one angle at each vertex, just like we have identified in our pentagon, is 360 degrees. So again, let me reread that. The sum of the measures of the exterior angles of a convex polygon, one angle at each vertex, is 360 degrees. And that's always true, no matter what type of polygon that you have. It could be a pentagon, it could have 12 sides, it could have 20 sides. No matter what type of pentagon you have, all of the exterior angles, if you add them together, will always equal 360 degrees. Okay, so let's put these theorems into practice. With our first example. Our first example wants us to find the value of x. So we see that we have a quadrilateral here. We've got 3 of the angles given to us. We could use either the theorem of interior polygons to solve this problem, or we could use our corollary about quadrilaterals. So it's going to be easier for us to use the corollary of quadrilaterals for this particular example. However, like I said, we could have also used the theorem about polygons and interior angles using n equals 4. But since we already know that our corollary tells us that the sum of the quadrilateral interior angles of a quadrilateral equal 360, we can just use that equation right there. So we've got 360 degrees. It's going to equal x plus 89 plus 92 plus 75. And when we solve for x, we'll end up finding out that x equals 104 degrees. And we're done. There's our answer. Okay, moving on to the next example. We have to determine if a regular polygon can have the possible interior angle measure of 165 degrees. So this means since it's regular, we're given the information right here that it's a regular polygon. That means that all of our interior angles are the same. So that means every single interior angle will have 165 degrees. So is there, in fact, a regular polygon that can have this measure? So we're going to have to use our equation from our interior angles theorem, which says that n minus 2 times 180 will give us the sum of our interior angles. But we also know that that would be 165 degrees times n. Okay, so when we solve this out, multiply and distribute, we get 180 n minus 360, that's 2 times 180, equals 165 n. So using our addition and subtraction properties, we now have 15n when we subtract 165 from both sides equals 360 when we add 360 to both sides. Dividing both sides by 15, we are able to solve for n, and n is a whole number, n would equal 24. So because this is a whole number, it's an integer, that means that we can in fact have a regular polygon with interior angle measures of 165 degrees. And that specific polygon would be a 24gon. So yes, we can have a polygon, and that would be a 24gon. Okay, well that's it for today. Hopefully you guys learned something new, and I look forward to seeing you guys in class later this week. Have a good one. Bye-bye.